Okay, welcome to this demonstration of EngineRoom software. My name is Chris Dunham. I'm the Managing Director of Carbon Descent, and we developed this piece of software, EngineRoom, and I'm just going to, in about 10 minutes, quickly take you through the functionality of EngineRoom. EngineRoom is a piece of software which is basically designed to help you understand the feasibility of combined heat and power, or CHP. So just a few words of introduction. The way EngineRoom works is it assumes that you have a base case, and the base case is that you're using boilers to provide heating and hot water, and you're importing electricity from the grid. And it then models CHP, the introduction of CHP, against that base case. So it shows savings in terms of financial savings and CO2 savings against that base case. So this is the basic, the main menu. So here you can see the options or the buttons that you need to go through in order to get to the calculate button where you get the answers. You can do simple or detailed estimations, and you can model an individual building or community heating. And if you, on any of these pages, if you just press this button here, it brings up a help menu that explains what's going on what the options are on what page. So you can see here, for instance, if you choose an individual building, you're basically assuming that the building owner owns and operates the plant, and the calculations of savings are shown in terms of offsetting the heat and electricity use within the building or site. If you choose the community energy option, you're assuming that a separate organization is operating the plant, such as an ESCO, and they are actually selling heat and electricity from the plant to customers on the site. So I've set this just the simple individual building. I'll leave it on detailed estimations, and we'll start going. So load profiles. So under each of these buttons you get various options, and in this case what you're trying to do is generate profiles of demand for electricity and heat that you're going to model the CHP against. So there are various ways you can do that. You can estimate them in the software, and there are two options here. So technical option, you would actually put in such things as the U values of different elements, and press estimate demand profiles. It would come up with some profiles for each month of the year. It's a typical day in each month of the year, and then you could say, I want to use those in my analysis. I'm going to say no. Another option, slightly simpler, would be to use benchmarks for different types of buildings. So here you can see different types of buildings you could model, and it will pick up benchmarks from a benchmark database, and then use typical demand profiles to create a picture of what the sort of hourly profile of demand would look like. And you can adjust those slightly using these options here. And then most simply, you could simply choose this option of entering the load profiles, and then copy and paste them in from some other source. Or you could you could put in the total annual consumption, say, if you knew that, and it will then spread that around over a year on a flat rate basis, or you could do the same on a monthly basis, and put in the figures by month. So I'm just going to go back to yearly, so we've got a completely flat rate picture of heat and power. And so that's our load profiles done. So that typically that's the most sort of time consuming bit of the picture, but if you've already generated them, or if you're happy to use something quite simple, then that can be done quite quickly. energy tariffs. So here you would choose your tariffs. If you're modeling the community energy option, you would need to set these prices down here, but as we're not, these are what you're selling heat to the customer for and what you're selling electricity to the customer for, and you may be paying administration and distribution charges to do that, so you could model those in there, but we don't need to fill this in for the individual building option. The owner of the building also owns the plant, so you're just looking at effectively the savings you're making from offsetting electricity that you would have had to buy in from a supplier. So, but you may be exporting as well, so it's unlikely that your CHP will follow your own power demand exactly. So you've got a choice of, you can set prices for import and export of power. So this is what you're offsetting that you would have had to buy in. This is what you're getting for export. So you can do that on a very simple basis of a flat rate price, or you can do something more complicated and go for a sort of seasonal time of day tariff or something in between, a kind of day-night tariff. But let's return to our standard tariff. We're going to choose a standard export tariff. We're going to have natural gas as our fuel, cost of the gas in there, and this is what it uses to calculate what the boiler plant would have used had you been using a boiler plant to supply this heat. So change this boiler efficiency to 80% perhaps. Cost of gas is the same as the cost of the gas for the CHP, and we set our energy tariffs. Moving on to the next button, here you're choosing which CHP plant you want to run the analysis for. So you've got two options here. So typically we might start off by comparing a range of different engine sizes. So we've no idea at this stage what engine size would be most suitable. So let's choose some, and you can choose as many as you like here. I'm just going to pick a few and so on, and you can actually edit this database and go in and put in more engines if you wish. Down here you can choose the control strategy, so you could choose heat-led or power-led typically. So heat-led, it means it tries to follow the heat demand profile. Power demand, it follows the power demand profile and then would reject heat if it needed to. Here you can specify what times the engine is going to run, or you could choose it's going to run continuously. So let's say it's going to run from 7 until midnight. Obviously, the characteristics of the engine will in some way determine whether the engine runs or not. So it won't. Its output can't fall below its minimum turn down, for instance. So financial information, moving on to this option. So here you can set the project life. So we might choose 15 years, 25, the discount rate, public sector discount rate there, 3.5%, inflation, and so on. Here you can model capital costs. So what the project knows, or what the software knows at this stage, is that you've chosen a range of engines, and it knows from the database what the capital cost of those engines are, what the maintenance costs of those engines are, and what the installation costs of those engines are typically. But there might be a whole set of other costs that you need to put in here. And for instance, it might be typically the cost of engineering is 10% of the overall of the CHP cost. But for some of these costs, you might choose to model a fixed cost and say, well, the cost of the community heating network that I'm going to put in, let's make it say 500,000. That is fixed. It doesn't relate to the engine size. It's just a fixed cost that you've worked out, and so on. So you might go through and model these in detail, either using this percentage of CHP option or fixed cost option, depending on what is more appropriate. So here you can model other things: the climate change levy, ROCs, a CO2 value that might be relevant if you were a site that was where CRC applied. And here you can model depreciation and so on, and loans. So I won't include that. And finally, you can set your emission factors, and not only can you set them for CO2, you can also set them, should you wish to, NOx, SOx, and carbon dioxide and particulates. So now you're done. You've done your modeling, so it just all you need to do is press calculate. So here you can see that a sort of typical picture, well, looking better. Actually, the best engine size is coming out with a net present value of just over $1 million. There you can see is the 377 engine, and after that it begins to tail off. And here you can see the sort of picture of more detail of what's going on for these different engines across the top. So here's our 377, which looks the best. So here you're getting good heat savings, electricity savings, and here are your operating costs and so on. So you can see that detail. So interestingly, the net cash flow is slightly better for that engine than that one, but obviously taking into account the difference in capital cost, slightly better on the engine 377 kilowatts electrical. Here you can see a bit more detail, run hours, quality index, and so on. So you might also want to look at CO2, and as is often the case, the best engine financially isn't necessarily the best engine in terms of CO2 savings. So you can see a larger engine would give you better CO2 savings. So we now know that in financial measures anyway, that the 377 is our best engine for these profiles. So we're going to look at that in a bit more detail. So we'll choose that one again, press calculate, and here we can actually scroll through different months of the year and see those changing on these graphs. Well, they're not changing because we chose a flat rate for our heat and power demand, so there's nothing very interesting to see here, but you could be modeling something more complex in terms of the heat demand profiles. And here you can see our net present value. So here we've got our initial capital cost in year 0, takes us negative, and as we move through time with our savings that we're making from running the CHP, you can see we're improving. Year 13, we're having to replace the engine. It's worn out, so we've got a bit more capital expenditure, and back up again to the end of our 15-year project lifetime. And here you can see a bit more detail about this particular engine. You can also go through into financial appraisal, and you can just see the detail of our discounted cash flow over our 15-year project period. So here's our capital cost, and here are our incomes and so on, and our net present value picture there. So and obviously you could copy and paste this into another spreadsheet and manipulate it in there should you wish to. So that is essentially it. There's a couple more things. One, you can actually save out your project. So you can the variables that much of the variables that you've entered can be saved as a project file that you can then load back in if you want to open up the software again and start modeling. So that is essentially EngineRoom. Thank you very much for listening.